OK, so what's quantum electrodynamics, or QED as everybody calls it? It's the theory of light interacting with matter, where matter in this case means electrons, basically. So we've already seen how to quantize spin-zero particles, spin-zero fields, and spin-half fields. So what's left to do is quantize light, which actually was the original motivation for field theory. And, the quantum physicists in the 1920s knew that light was described by the electromagnetic field, and they wanted to quantize that. But as we'll see in the next two lectures, there's several rather tricky conceptual subtleties when we try to do this. They weren't really sort of figured out until the 1960s, how to resolve them. So what I'm going to do in this lecture, and for the first part of the next lecture, is just tell you how to quantize a spin-one field and get something sensible. And then at the end of the next lecture, we're going to add matter in the form of the spin, as we've already seen, see how it couples to light, and write down the full Lagrangian for QED. And then you're going to spend afternoons doing calculations of scattering amplitude. OK? So we're going to start just with Maxwell's equations. So by this, I mean Maxwell's equations in vacuum. So we're not going to have any sources yet. And we've already seen the Lagrangian. It's of the following form, where this guy is usually called the field strength. And it's not itself a fundamental field. Instead, it's constructed from derivatives of this, what's called a gauge field, A mu, minus d mu, A mu. OK? So the equations of motion come from the usual Euler-Lagrange equations. The action doesn't depend on A itself. It just depends on the derivative of A. So you just get one term. Hey, Neil. How you doing? Of course, we should add to this the Bianchi identity. So this is an identity that just follows by plugging this definition of f into here and noticing that derivatives commute with each other. So d mu is the same as v nu d mu. Okay? So that's identically holds. And these set of equations are called Maxwell's equations. OK, so this was set as an exercise in the very first week to just derive Maxwell's equations from this Lagrangian. But is everybody happy with this notation, these ideas? Yeah? OK. Good. So what we want to do is quantize this Lagrangian. And we're just going to do the same steps that we've been doing over and over again for scalar fields and for spinor fields. But there's going to be a problem. And you can see the problem immediately because this guy here, this A mu, which is going to be sort of the field we want to quantize, has an index that takes 4 values, 0, 1, 2, and 3. So if we were going to quantize naively, you might think that, well, there's sort of basically 4 fields, and each of them is going to give rise to a particle. So I'm going to have a photon which somehow has 4 possibilities, or 4 degrees of freedom. But that's not right. Right? And we all know that photons have 2 degrees of freedom, the polarization states. So somehow, when we quantize this guy here, which has 4 degrees of freedom, or at least certainly has a label that takes 4 values, we've got to lose 2 of them in the quantization process. And that's going to be sort of fairly subtle, and that's the difficulty we'll walk through today and tomorrow. Okay? So the massless vector field A mu, where mu goes from 1, 2, and 3, has 4 degrees of freedom. But we know from observation that if this is really going to match the real world, it better just end up giving us 2 degrees of freedom because the photon has 2 polarization states. Okay, so this whole lecture is going to be to figure out this counting, how you lose 2 from 4 to end up with 2. Okay. So to begin with, there's 2 comments I want to make about how we're going to lose these degrees of freedom. Okay. So comment 1. By the way, all of what I'm saying at the moment sort of also holds in the classical theory, so you may have already come across it in courses on electrodynamics. So comment number 1 is that the field A0 is not dynamical. In particular, this means that there's no term which depends on A0 dot in the Lagrangian. Right? The field strength is always anti-symmetric in the derivative and the value of A. So there's never any A0 dot. But that means that the Lagrangian isn't really, well, it means that A0 isn't really allowed to fluctuate on its own. Okay? The value of A0 is entirely fixed by the values of all the other fields. So this means, hi. Okay, so if we know what the spatial components of A are and their time derivative, so this is like, as always, position and momenta, then we don't get to, also include information for A0. It's basically fixed completely by what these guys are doing. Okay, and this just follows from the equations of motion. This is Maxwell's equation in vacuum, which of course is one of these equations when the nu is 0 here. Yeah, please.
In writing down the action, we just wrote -quarter f mu nu, f mu nu. Yeah. But that doesn't seem on the face of it to give preference to any component. So, I mean, and that argument comes from a different form.
The preference of the component is the fact I've chosen to focus on the dot here, being time, rather than one of the spatial directions. Okay, so if there's no A0 dot, if I focused on, say, A1, it's true that there's no D1 A1.
Oh, I got it.
Time is special.
Got it. I see what you mean.
Okay, so this is the equation as we learn it in kindergarten. This is the equation when we put in the values of A that comes out of that. And we can solve this equation. So A0 of x, we can solve it in terms of Green's functions, basically. Hey, Eric. Okay, so this is all in vacuum. No sources. And A0 is determined exactly by this function grad of A dot, okay, by the following integral formula. That's a divided by. Okay, is this clear? People happy with this? Yeah. Okay, so we started with what we thought were 4 degrees of freedom. There was A0 and the 3 AIs. And we've now learned that basically because there's no A0 dot, A0 is kind of going along for the ride. It's not an independent degree of freedom. It's governed precisely by what the spatial A's are doing, and that when we quantize, we're likely to just have 3 degrees of freedom instead of 4. Russ?
All 4 vectors only have 3 degrees of freedom? Because like the P4 vector, the 0 component's also constrained by...
It's also constrained
it seems like
for real particles.
Yeah.
But of course, it's not when the particles run in the loop, then it takes anything in line.
Okay.
So it really depends on the context.
So it's just a coincidence they both have this equation that constrains the 0 component.
Yeah, and I think they're on very different
Okay,
fronts.
so I shouldn't think.
In particular, we've got down to 3, but we've got to still lose another one. So.
Right, so yeah, so that just goes to show that you don't equate things.
However, let me not confuse the issue by caveating that thing. Yeah, they're just we can chat on special on caveats. Yeah.
Why can't you just say that we have 4 fields and we have these 2 equations, that the equation of motion, the Bianchi identity, and so that reduces our degrees of freedom by 2?
Because you would have said exactly the same thing for the scalar field. You've got 1 degree of freedom and a time order equation, which reduces your degrees of freedom by 1, but that's not going to buy you anything, right? So the reason is that, I rubbed it out. The equation of motion is a second order equation of motion, not a first order. So when we mean degrees of freedom, we mean how many degrees of freedom are there subject to a second order equation of motion, which then allows you to specify a position and a momenta as initial conditions. So it is true that if you have a first order differential equation, that kind of cuts down your degrees of freedom by half, because we saw this for the spinor field. What we think is the momenta is actually not something dot, but it's just a complex conjugate field. So that does cut down the degrees of freedom. But yeah, second order equation. Now the Bianchi identity, that's another issue. That is kind of going to be.
So here you're specifically taking your spin one particles only concentrating on photons, which are the massless ones. Mm-hmm. Is there a way to do all, like keep a master in Lagrangian and do everything where m equals 0 is a special case that removes 2 degrees of freedom?
Yeah, so you can quantize massive spin one particles, but n equals 0 really isn't a special case.
Oh, okay. So you really have to separate them into...
Yeah, so the correct statement is that if you have a massive spin one particle, it does have 2 degrees. And a massless spin one particle has 2 degrees. So there's actually a discontinuity as n goes to 0. So n goes to 0 should be 2 degrees. And here we're just going to do the massless case because
the argument in A naught is that just 3 vector x, or should that be 4 vector x? Because
yeah, it's probably 4 vector x, but the t is the same as the t here, right?
In which case it wouldn't be a 4 vector argument to
not a 4 vector
naught.
integral.
No, on the left.
I think it's going to be this, right? This is x comma t, and this is x. Okay, so A naught is just kind of going along for the ride. It's following whatever the other guys are doing. What's more interesting is how we go down from the 3 degrees of freedom to the 2 degrees of freedom of polarizations. And this is this follows from an observation which is really one of the key observations in all of theoretical physics. It's the thing that generalizes to all other theories that we know. So I'm going to take some time going slowly over this. So the observation is the following. It's that the theory has a very large symmetry. And I mean very large symmetry. And the symmetries are of the following form. You take your gauge field, and you add to it any function lambda of x that's differentiated by d mu. Okay? And we're going to require certain properties on lambda of x, like it dies off suitably quickly at infinity. But you know, basically, it's any function you like. Okay, so why is this a symmetry of the Lagrangian? Well, let's just plug it into F and see what happens. So the field strength changes in the following way. But you see the d mu d nu here cancels the ones with the derivatives the opposite way around there. Okay, so the field strength doesn't change, so the action only depends on the field strength and not on A, so the action doesn't change either. Okay? Yeah.
In the notes, you made the comment that lambda must die off fast enough at infinity. Looking at this line, it's not really obvious why.
Yeah, that's so you don't need it here. This will become clear in the next one. Okay, so this is data. People have probably seen this before. Most people seen this before. Okay, so this is. Okay, firstly, why do I say this is a very large symmetry group? All the other symmetries we had, you know, you get to take a field or something and act on it by some action that depends on a single number. You know, I get to rotate the whole field by 30 degrees or 60 degrees or 90 degrees. It's a one-parameter family that I get to decide what to do. Here, I get to act on the field, but I get to act on it with an entire function's worth of operations, not just a single number.
So we've gone from ALOF 1 to ALOF 2.
Quite possibly. I would actually say we've gone from 1 to infinity. What's 1 in terms of aleph?
Are all of real numbers.
Yeah, no, I think the right way of counting this is that the usual symmetries depend on just one parameter. Okay? But this is a symmetry that depends on an infinite number, a continuous infinite number of parameters, any function that I like, which of course I can then multiply by an overall constant number. Okay? But any function. Okay. Now in this first lecture, I was really stressing the importance of symmetries, of what they buy you. You have a symmetry, it gives you a conservation law, and that gives you a conserved quantity. Okay? And we've made a lot of progress by this. But now we've got a theory that has an infinite number of symmetries, one for every function. So you might think, aha, we're in business. We've got an infinite number of conservation laws. But that's not the way it works. Okay? There's a crucial distinction between symmetries where the parameter can depend on space and the symmetries where the parameter doesn't depend on space. So all the ones that we've seen so far, translations, rotations, or perhaps more pertinently, the phase rotation of a complex field, the parameter in that phase rotation was just a constant. It didn't depend on space. Now we have a symmetry that where the parameter is itself a function. These symmetries have a name, a couple of names. They're sometimes called local symmetries, or they're sometimes called gauge symmetries. The term gauge symmetry is more commonly used. And the thing I want to jump up and down and stress to you is that they're not symmetries. Okay? The names are very, very misleading. So let me explain what I mean by this statement. A symmetry of a system is where you have the system sitting here, and you can do something to it, like move the box to here or rotate the box, and the physics doesn't change. If you could figure out what was going on here, you can figure out trivially what's going on here. The physics is exactly the same. So said another way, you take one physical state and the properties of that are equivalent to another physical state. That's what's meant by a symmetry. That's not what's going on here. This change from this A mu to this A mu should not be thought of as changing from one physical state to a new physical state. These should be thought of as exactly the same configurations. And the things we call gauge symmetries, or local symmetries, aren't symmetries, but they're redundancies of your description of the theory.
So in that case, then the name symmetry group is also misleading?
Yeah, but it would be much easier in teaching this if Weil, when he invented this idea, and referred to it as a gauge redundancy instead of a gauge symmetry. But gauge symmetries, or local symmetries, to be contrasted with what's usually called global symmetries. They're the ones we've seen before. Global symmetries give rise to a conservation law and change one physical state to a new physical state. Gauge symmetries are basically a redundancy in your description of the system, and the new state you get is to be thought of as exactly the same as the original state.
So for wave functions in quantum mechanics, the phase, changing the phase globally is a symmetry or a redundancy?
Yeah, so in quantum, yeah, that's this distinction between local and global is good in field theory. In quantum mechanics, the redundancy is actually the global phase of the wave function, not the local phase of the wave. But that, as always, is because in quantum mechanics, you know, spatial position x is on a different footing from what it is in field theory. Like it's sort of an operator, if you like, rather than just a wave. Okay, let me write this down. It's important, so I actually will write this down. Okay. So this is an infinite number of symmetries. Okay, one for each function that you can write down, lambda of x. So these are called local symmetries or gauge symmetries. And they're not symmetries. Certainly not symmetries in the sense that we've been meaning it so far in this course. So they do not take one physical state to a different physical state. So instead, they are to be viewed as redundancies in our description of the system. Okay? Yeah. Yeah, great. So you could think, yeah, we're just doing the wrong thing. Right? What we should do is think in terms of F mu, which is really electric and magnetic fields. I thought they're what we measure. So why not just quantize the electric and the magnetic field? The problem is that doesn't contain all the information that is contained in the A's. So there's this thing called the Aharonov-Bohm effect in quantum mechanics, where a particle moves in a region that doesn't have any magnetic field, but nonetheless it's affected by a magnetic field elsewhere because there is a non-trivial A mu. So it's not quite true to say that say that you can just replace the information in A mu with the information in E and B.
So
There
my,
is information in here which is
my question was, though, then they are different physical states by making a transformation.
no, they're not physical.
They're not physical.
So what's physical is,
Is the difference
is
between things.
anything you can write down in terms of A mu, which is invariant under this transformation, which isn't effective. Now, one of those things is E and B, but what Aronoff and Rome showed is there's actually something else, which is basically the integral of A mu dx mu around any contour, and that this doesn't change under this, but it's not captured in E and B. So there's this mathematical statement is that there's other gauge invariant quantities which are not E and B. There were a bunch of hands. Yeah.
So, but for the Aronoff vector, you can write the vector potential as the gradient of the lambda, but with the lambda that's multi-valued.
Right, the vector potential. Yeah, exactly right. But this, and as I defined it, this should be a function over space.
Okay.
There's lots of beautiful subtlety about how you can construct gauge invariant things out of A's that you can't write in terms of B's. It's a lot. For example, you can construct magnetic monopoles this way that violate that Bianchi identity. Rad.B equals 0. We play around with this about multi-value things, and you can construct magnetic monopoles. And indeed, we think they exist in certain fields.
So what's a good book that talks about all this stuff?
Yeah, most decent field theory textbooks have sections at the end about solitons, magnetic monopoles. Yeah, that's sort of where this is heading. I suspect somebody somewhere in this next year will discuss this. But it's a beautiful story, and it gets even more interesting. You know, the weak and the strong forces are described by A's, which are matrices, 2 by 2 matrices or 3 by 3 matrices. They live in SU2 or SU3. And they have something similar to this, and then it gets even more wonderful. You know, there's a lifetime worth of study and understanding. Callum, you have
I think there's something about what you're talking to Henry.
I think
When you get given a gauge symmetry, you're also at the same time being given a global symmetry. Which is
I'm going to mention that in the next
right.
section, yeah.
I think that's the sense in which there is something physical about you've been given that equation.
Yeah, that's actually only true when we include matter, but as always, there's going to be caveats to this. But we'll get there in the next section. At the moment, this is the state. This is the message. Other questions? Okay, let me just sort of show you mathematically why, even in the classical theory, that this is a good interpretation, that this is a redundancy. So to see this, we could look at well, we could notice that Maxwell's equations do not determine the evolution of A. Okay, so these are Maxwell's equations written in terms of A. This is the second order differential equation that you get. This is just d mu f mu nu equals 0. But this is not invertible. And in particular, it annihilates if you put anything on the right-hand side here of this operator that's of the form d derivative of some function, it's annihilated by this operator. Okay? What does that mean? It means that we've got no way of sort of uniquely figuring out what A is doing. We've got no way of knowing if a given A at some initial time evolves to a particular A at later time, or that A plus something of this form, because this operator just doesn't distinguish between those two cases. Okay? So, yeah, Prasanna.
Probably a sort of unrelated question, but since we are on the topic, they recently discovered magnetic monopoles in spinets.
Yeah, it's a bit of a swindle, but yeah.
Okay, so my question was, we saw how charges can emerge, the concept of charge can emerge from the symmetry the phase, the invariance and the phase. If the electromagnetic force is one force emerging from a mu, why are there magnetic monopoles with north and south, and electric charges plus and minus? Why are they two different things?
So it's a mu which is distinguishing between electric and magnetic charges in substance. Actually, it really follows when you couple matter to this theory. If you work in terms of a mu, there's no way to couple magnetic matter. And the reason is that this grad dot B equals 0 is an identity. It's the Bianchi identity. So there are ways around it, but that's not really right. However, it's easy to couple electric matter. So it's the choice of a mu already, which is sort of distinguished between electricity and magnetism. By the way, that spin ice example, what's really going on is the following. It's easy to get two magnetic monopoles. What you do is you take a very long solenoid, and this is a north pole, and this is basically a south pole. And what you do is you make this so thin that you can't see. That's roughly what's going on in these experiments. It's a little bit more. What's actually going on is that they're claiming this solenoid between the two is actually becoming massless and
disappearing.
That's the claim. But it's not really a fundamental Dirac monopole. It's a way of making a solenoid and then the dynamics are basically masking the fact that these things are connected.
David, if there was a monopole inside a black hole,
yeah,
then the effect of that will also be observable.
Yeah.
Something that Malcolm Perry mentioned, he only mentioned electric charge being observable if it's inside a black hole. But he didn't mention it, but a monopole would also affect the space-time around it, right?
Right. I should say that I would bet that 99% of people working in sort of formal theoretical physics, quantum field theory, believe that magnetic monopoles exist, despite because they're really one of the robust predictions from every theory that we have that goes beyond the standard model of particles. Whatever you choose, grand unified theories or string theory, every single one just gives you a magnet. So I think they're there. I haven't seen them yet.
Then I'll ask the stupid question. Why haven't we seen them?
Oh, because they're heavy. Oh, actually, two reasons. One is because they're heavy, which means we can't create them in particle colliders. And the second one is because of inflation. So, if there were any lingering around right at the beginning of the universe, inflation just spreads them apart and moves them through space. So, they're not a part of Okay, so we've got this operator which doesn't, it's the evolution operator, and it doesn't tell us exactly what A is doing. So what are the choices? We can either say that, well, our theory isn't well defined. It's one possibility. Or we could say, actually, this is okay, because if we identify physical states, well, if we identify A and A plus d lambda as the same physical state, then we don't care that our evolution operator didn't distinguish between them, because it's the same physics. Okay. And I should say that this trick, nature, to write out all the theories we have of nature, we have to somehow work with objects that we couldn't possibly observe. There's always redundancy in all of our theories. So this is the redundancy in the gauge potential, in electromagnetism. The same thing is there in strong force to weak force. The same thing is there in general relativity. We're never going to measure electricity, right? It's not diffeomorphism. You can only measure things that diffeomorphism invariant in general relativity. And as you pointed out, the phase of the wave function in quantum mechanics is non-creative. So I don't know why nature picks this trick. You're obliged to work with variables that are never going to be physical, and you're obliged to impose these gauge symmetries to sort of identify them. It's a beautiful trick. It means there's lots of nice things that happen. I think we're missing some deep reasons for why this. Okay, so there's a nice picture we can think of the phase space of the theory. Okay, so this is the phase space of the theory. Every single point here corresponds to a different value of AI and AI dot. Okay, so this is the phase. Oh, yeah. Let me call it the enlarged phase space for reasons that will become apparent. Okay, so this is basically the space of any function you can write down, AIs and AI dots. But having this gauge symmetry means that if you pick one function, then actually there's a whole class of functions that are related to it by a gauge symmetry. So everything that lies on these lines is to be considered physically equivalent. So these are, if you like, gauge orbits. So if we want to work with the theory, every single point on this line is equivalent to any other point because they're all related by this d mu lambda. Same for this line. So what we have to do if we want to work with, actually make calculations, is typically just make a choice of one particular configuration from this line, one particular configuration from this line, and so on. So we pick some choice where we want to make a good choice, so we guarantee that we get exactly one from each of these lines. Okay. So to calculate, we'll often have to make a gauge choice. And that's what this dotted line represents. It's picking a representative sample from each of these gauge orbits. Okay. Different choices are often referred to as different gauges. Another question?
Why don't we use like an equivalence class?
Yeah, you just do that. Right, so that would be, we'd say that was the gauge invariant way of calculating. And you can use should. Often you won't be able to. Often there won't be good ways to get this in. And doing the kind of calculations we'll do here, which is quantizing the field and seeing photons, that's an example. You've got to make a gauge choice. In the path integral formulation, you often it's hard to see particles in the path integral formulation, but other calculations, some calculations can be done in gauge invariant way, but often again. Another question?
Is it literally impossible without making a gauge choice, or simply impractical?
I think that for most calculations, people don't know how to.
Okay.
You can write down formally mathematical expressions in terms of the path integral, but nobody knows what to make.
Oh, yeah.
Okay, let me give a couple of examples. The first one is called Lorentz gauge. And it's the following choice, that we'll pick a set of orbits along here such that the gauge fields A mu obey the following condition. Okay? Let me just convince you that we can always do this. So suppose we started with some A mu prime. This prime shouldn't denote differentiation, by the way. It's just a different A. And so you take somebody gives you a configuration, you differentiate it, sum over the mu's, and you find that it's some function f that's non-zero. Okay, what does that mean? That means that somebody's giving you a configuration that lies here. What you want to do is make sure there's a gauge transformation to take you here such that the new configuration obeys this. Okay. So that's pretty easy. We act with a mu, which is related to the first guy by a gauge transformation. And all you've got to do is make sure that this gauge transformation satisfies the following. It's almost like a massless Klein-Gordon equation, but you pick a lambda so that it's just the Laplacian, the Minkowski Laplacian is equal to minus f. Okay, you can always find a lambda that does that, so it's trivial. Okay, but by the way, people will often insist that this is the wrong name for this gauge. This gauge was first written down by Ludwig Lorenz, not Lorentz, when Lorentz was about age 14. Okay, so it was written by another guy. However, he had the misfortune to create a gauge that happens to be Lorentz invariant. Okay, so I think this is the reason why everybody calls it the Lorentz gauge. If you read lots of textbooks, they all start complaining that you should call it the Lorentz gauge. Poor old Lorentz, he doesn't get enough credit. You know, the guy's dead. I don't care. I think it's a great name because it tells you that it's Lorentz invariant. Okay, that's the defining property. Yeah. No, so I'll mention one now. But what happens is you would do the calculation and nothing would look Lorentz invariant. But at the end of the day, your answer has to be Lorentz.
Okay, so it doesn't, obviously, because if the gauge doesn't matter, it doesn't matter if it's not Lorentz invariant.
Exactly, yeah. Now, I've mentioned this before. Sometimes you run into trouble because this is an example where there had a symmetry, Lorentz invariant. You had to do calculations. You decided it was best to work in a gauge that didn't preserve that symmetry. Now, sometimes it happens that in quantum field theory, if you're doing calculations that don't look as if they preserve the symmetry, they actually don't. And that's an example of what's called an anomaly. So it typically doesn't happen to Lorentz symmetries, but you often find a need to pick gauges that break other symmetries. And sometimes then it's not possible to get problem. So this is an area of thought with danger. But it's also some of the most interesting parts of it. Okay, in some sense, this actually isn't such a great gauge. Yeah, Tigo. Or you're just thinking your hand on. It's not such a great gauge because it doesn't uniquely pick a configuration along this line. So in some sense, this gauge choice is sort of more like this. Okay. So this condition doesn't pick a unique representative from each gauge orbit. And the reason is clear, that we can always act with another gauge transformation where lambda just satisfies d mu lambda is 0. And there are solutions to that equation because this is, because we have signature 1 minus minus minus, so you can basically have traveling waves. So can always act So this is a residual gauge symmetry. Even after we fixed this gauge, there's still this left over. Okay, let me give another example of a gauge choice. Coulomb gauge. This is also called radiation gauge sometimes. Is where you pick this requirement. So actually, you can think of this as a subset of Lorentz gauge. You first fix Lorentz gauge, then you make use of this residual gauge symmetry to fix yourself to this. Okay, and it's exactly the same argument that I've been making. So you can check this. So we can get to this. By making use of the residual gauge symmetry in Lorentz gauge. So also note that when grad dot A is 0, remember that A0 was fixed entirely in terms of what A was doing. Okay, I wrote that equation squeezed into this part of the blackboard earlier in the lecture. So when grad dot A is 0, A0 is also strictly 0. Okay? Okay, so you can see immediately that this is an example of a gauge that breaks Lorentz symmetry. What happens is if you work in this gauge, things are kind of ugly because nothing's Lorentz invariant. But it all works out okay. You get to the end. And of course,
why are you choosing A0 equals 0?
Oh, I'm not choosing it. This is an implication of choosing this gauge. If I do this, remember I had this equation, A0 is equal to the integral of grad dot A dot over x minus x prime. So I'm just plugging into this. Other questions? Yeah.
That extra residual gauge symmetry that you said to use, is that what's going to break Lorentz invariance, basically? That you have?
Yeah, I picked a different specific lambda here, which kills this, basically. Other questions?
Is that unique?
Yeah, once you've got this, you've now got a good slice.
So there's only one solution to.
Yeah, I think because what you've got left are things that have to obey grad squared lambda equals 0. But now this is there's no minus signs coming here. This is really just the Euclidean and Lassian, and that was the minus sign of the lambda. Okay, so a slight side remark. the same people that bitch and moan about Lorentz gauge being named wrong never complain that Coulomb gauge is named wrong. This guy died 60 years before Maxwell's equations were written down, so I'm fairly sure he didn't understand gauge symmetry and such like. So, you know, I think they're both good names, and we should stick with them. It's true, of course. You know, he did, but you know, he's got his name on enough things. If somebody comes up with a gauge, okay. Yeah. So these two gauges sort of are representative of things that you're going to see over and over again in theoretical physics. Okay. We've got the Lorentz gauge, which looks very nice. It's all, you know, it's all Lorentz invariant. It's a simple equation. When we do the calculations in Lorentz gauge, things are going to be very, very elegant and pretty. However, the fact that we have this residual gauge symmetry left over is going to cause us some headaches. Okay, we're going to have to work quite hard to think about how to deal with that. On the other hand, we've got Coulomb gauge, which isn't Lorentz invariant, but it has the advantage that the physical degrees of freedom are immediately apparent in this gauge. Because we've set A0 to 0, so we just forget about it. And A has to satisfy this single condition, which basically means that there's no longitudinal polarizations for photons. The photon's going in that direction, it's got a wobble in one of the transverse directions. Okay? So these two conditions have immediately killed our 4 degrees of freedom down to the 2 that we want, the 2 polarization states. So if we quantize using this gauge, we're not going to have to worry about degrees of freedom. There's always going to be 2 from the outset, but everything's going to be very ugly. Okay? So there's a slight payoff here as to which we choose to do. And this is an issue that you'll see coming up over and over again. There's different gauges, in one of which it's usually ugly and messy, but the physical degrees of freedom are very clear and apparent. That's Coulomb. And the other one of which all the symmetries are manifest, but you have to work harder to understand the physics. Okay?
Question. My question is, if you have A0 as the integral of 0,
yeah,
the integral of 0 is a constant.
Oh, you're worried about
a constant. Why? Because as you choose A0 to be 0, that's why you use a degree of freedom.
I could always add a constant here, and this comes just from acting with plus g lambda, where lambda is some constant times time. Okay, so any constant I could always.
So that constant alone is a degree of freedom because I can choose any constant.
No, it's not a degree of freedom because I can just remove it by gauge transformations. And you know that this is the first example of a gauge transformation that we learned in school. It's the statement that, you know, when you're doing voltages in high school, you know, the actual voltage doesn't matter. It's really just the potential difference that matters, right? And that's the statement that A0 could be what you want. It's the difference of A0 and 2. Okay, so are we clear on things? Any more questions before we terminate? Okay, so at this point, we've got a choice, and the choice is whether we quantize in Coulomb gauge, where the physical degrees of freedom are clear but everything's messy, or whether we quantize in Lorentz gauge, where there's a bunch of subtleties and it's fairly sophisticated, but the answers are elegant. And so we're going to do the latter choice. We're going to quantize in Lorentz gauge. It's conceptually more difficult than Coulomb gauge, but the reason I'm going to do it is because these difficulties are honest difficulties. They're problems that arise in all of gauge theories, and you have to know how to confront them and how to deal with them. And so somehow working in this way, it's messy and it's a little bit too easy. We're sweeping things under the carpet. So what I want to do is just show you what these difficulties are and how we cope with them.
Is there a way to use like light tone components? Like A0 plus AX?
Yeah, that's often very useful. I don't know in this context. I mean, you could always do it, so I don't know if that's going to be a useful thing to do. I suspect it would be, actually. I suspect it would be rather analogous to Coulomb. But we're not going to do that anymore. Okay. So, Lorentz gauge. Okay, so if we impose Lorentz gauge, then the equations of motion that the A mu's satisfy are extremely simple. Okay. Each component of A mu obeys the massless Klein-Gordon equation. Okay. If you look at the full operator I wrote down before and insist that A mu obeys this, one of the terms drops out. You've just got this. Okay, so very easy. Okay, so our strategy to quantize this theory is going to be the following. We're going to quantize a theory which obeys the following equation of motion. So what I'm going to do is write down a new Lagrangian whose equation of motion is this. Okay? We'll quantize that theory. We'll see that it doesn't make any sense for a particular reason. However, what we've got still lingering is the fact that we have to impose this, and we still have this residual gauge symmetry. And so we're going to see why it doesn't make any sense, what the difficulties are, and then we'll see why imposing this equation here and this extra residual gauge symmetry saves us from these problems. Okay, so that's the strategy we're going to do. So let me give a name to this. Strategy is to quantize a theory with these equations of motion. And only after we've quantized it, we're going to impose this condition and the residual gauge symmetry condition.
I thought the equations of motion that you wrote down over there already did impose partial mu A mu equals 0 to get the reverse.
No, which one? The one that I had on the box here, but I said was not reversed.
No.
These ones. Yeah, these ones. Yeah, let me write down the next thing, and then
Okay.
maybe I'll become clearer.
Okay, so we're going to work with this Lagrangian. So what's the purpose of this Lagrangian? Well, if you compute the equations of motion from this Lagrangian, it's equal to this. Okay? Now, if I work with this Lagrangian, I get these as the equations of motion immediately, but they're only going to agree with Maxwell theory if I subsequently impose this Lorentz condition. Okay? So I think this is the answer to your question, Chris. If I get Maxwell theory and then impose this, I get these, but I'm going the other way. I'm starting from this, getting these, but then I still need this to agree with Maxwell theory. Okay? Which you can sort of see because this term just disappears if I impose this. But I'm going to impose this afterwards, not before. Okay, classically it's exactly the same. Quantum mechanically, we need to impose this afterwards. Okay, is this clear? People puzzled? No, there's no dynamical field here which is going to impose this. It's just a new Lagrangian that I put up to give these equations. Okay, so what do? We just treat this as the usual Lagrangian for A, and we just run through this machinery we've been doing over and over again. So the first thing is to compute the momenta conjugate to A. Okay. It's worth just pointing out something here. These are the momenta coming from this Lagrangian. If we now impose the Lorentz condition, we find that the momenta conjugate to pi 0 is vanishing. Okay? That's the same statement I said before, that if we just look at the Maxwell term, there's no A0 dot. So A0 is not dynamical. Okay? So if you quantize in the Coulomb gauge, one of the problems you run into is what do you do about the fact that pi 0 is 0? But here we've sort of circumvented that. We've worked with a slightly different Lagrangian. We get that pi 0 is equal to this, and we're only going to impose that it's actually vanishing later in the proceedings. Okay, what do we do now? We quantize. That just means we impose canonical commutation relations. Okay, we're going to work in the Schrodinger picture to begin with, because there's little twiddles under the arguments here. So these are the standard commutation relations that we would impose. Okay, now we work out the mode expansions. I'm going to write them here just because I might need them later. Okay, so these are really the same things we've seen before, but let me just walk you through a few subtleties. There was always EPs here before, the energy of the particle, but this is a massless particle now, so its energy is equal to the modulus of extreme momentum. So that's why these are here. There's a difference in a minus sign here. That's just convention at the moment, but it's going to be the useful thing for later. It's because these things have a mu index, which is a Minkowski index, and so there's sort of minus signs that arise when you pull the mu label up and down. But for now, it's just convention. Polarization.
Has a mu, but it should have a mu.
Should have, yeah, this should have a mu. Yeah, there's A's and A daggers instead of B's and C's because this is a real field, it's not complex. So the only new thing are these guys here. So these are polarization vectors, as Callum just said. Okay, so what's going on here? Remember when we quantized the spinner? The spinner has a spinner index, alpha. But we didn't put the spinner index on the creation operators, the B's and the C's. What we did was we sort of came up with a basis for spinners and then wrote the spinners separately and put the little basis index that we called S on the B's and C's. Okay? What we're doing is basically the same here. So these polarization vectors So this is a basis of 4 vectors spanning the vector space of mu running from 0 to 3. You might think it's a little bit redundant. The key is that we want to define epsilon 0 to be timelike. And so by the way, each of these are 4 vectors. These are four vectors. So there's a mu index here, which is the vector index, which I'm suppressing. Okay. To be space-like. And so we'll pick these to be some orthonormal basis, where orthonormal so there's 4 vectors, there's four vectors. And the first 4 is labeled by lambda equals 0, 1, 2, 3. You dot them because they're each 4 vectors. And so these 4 vectors are, must be an easier way to say this. This set of, I want to say the word 4, but then not follow it by the word vector, because then it sounds like it's a 4 vector. These sets of vectors are orthonormal in this sense. Okay. Sorry, that's really muddled. The key reason for doing this is because we're going to have one further choice. Sorry, say that again?
The cardinality 4 set of vectors.
That doesn't sound a whole lot clearer. We'll further pick the third vector to be the longitudinal polarization. Okay, so this is really the key step. So these polarization vectors depend on the momentum p of the photon. Okay? Just like the spinner vectors we put in there that were called u and v, they depended on the momentum of the spinner. So it's exactly the same concept. The reason for doing this is that we want to just decide that the third vector, the third of these 4 vectors, is going to be along the direction of the momentum of the photon. Okay, so epsilon1 and epsilon2 are always, for any momentum we choose, they're going to be functions of the momentum, but defined so that they're always if the momentum's going that way, they're always the transverse guys. Okay. So let me just give an example. So if the momentum is it actually in the third direction? Then these are sort of a sensible, well, the kind of basis you might immediately imagine. Okay. Whereas if we pick the photons going in a different direction, you always want epsilon3 to be such that it's moving in the direction the photon is going. Okay. The advantage of this notation is now that A1 and A2 are always going to create photons that are polarized transverse to the direction of motion. But they're the ones we actually want at the end of the day. They're the physical ones. So it's going to be A3 and A0 that will create states that we actually want to get rid of. But it's always going to be A3 from now on because the momentum dependence got soaked up in here. OK, so let me just push on for another 2 or 3 minutes, and we'll see where the problem lies. Is this clear? Any questions about polarizations? Yeah.
So in the vectors that you chose, you could rotate epsilon1, epsilon2.
Yeah, that's right.
That's where degrees of freedom are for the polarization? Or?
Yeah, or said another way, what's going to happen is I'm going to find out that for various reasons, A0 and A3 are not going to create states. The states are created by A1 and A2. So for each photon, I've got 2 possible states. Now I can act with cos theta A1 plus sine theta A2 to create some mixture of them polarized in different directions. Other questions? Chris?
So it's the label P that determines the frequency of what we're creating? So.
We'll turn it into the energy. Remember, what's in here is usually the energy.
Yeah.
Excuse. The way these 4 vectors are this epsilon 0 to epsilon 3, you're already imposing the condition that we want a 2 degree of freedom as a result instead of using it to prove it.
No, I'm kind of anticipating that. So at the moment, it's just notation. I haven't yet showed you that A0 and A3 are bad. We'll find out that they're bad, and we'll then show them that we should get rid of them. At the moment, I've just introduced some notation that's going to be useful.
What I'm saying is that what you are imposing on this epsilon 0 to epsilon 1 is already something that will end up in a case where we have it.
No, this is just a convention at the moment. So epsilon 1, so at the moment I've got 4 polarization vectors which are just anything like that. Yeah. And as we'll soon see, I'll be able to create, actually creation operators, create all 4 of these photons. Okay. But then we'll see that actually 2 of those photons are bad, and we'll see how to get them. But we're still going to create all 4 of these vectors. I'll do that. Okay, so this usual story, we have these computational relations. Yeah, it's going to be useful if I just move this new index downstairs. Okay, before I had the new index upstairs and there was a delta here, but of course these are really space-time indices, so it gets moved down and it gets replaced by a Minkowski metric. Okay, so all others 0. Okay, so this is the usual kind of commutation relation we've seen over and over again. You just plug these into here. So what's the problem here? The problem is that there's this Minkowski metric that appears on the right-hand side. Okay? And the Minkowski metric is indefinite. It's got pluses and it's got minuses. At the moment, I put a minus sign here, which means that for the spatial components, remember the Minkowski metric is plus, minus, minus, minus. So this minus sign cancels the minus sign here for the spatial components, and these look like good creation operators, or the usual commutation relations. But for the time-like component, when this is 0, this minus sign is looking problematic.
Is that because of the little problem we had earlier?
No, it's different from that, and it's a slightly different flavor. Let me write it on the board, and then I can talk a bit more. So for lambda is 1, 2, and 3, that's the space-like polarization states. We just get the usual commutation relation. But this guy comes with a minus sign. Okay, so it smells a little bit similar to what we saw for fermions, but it's really a very different physical issue, and it's going to be resolved in a different way. So we haven't talked about the Hamiltonian yet. The Hamiltonian isn't going to be unbounded below. That's going to be fine. What's weird is this minus sign here. And let me explain why it's weird. So if we define the vacuum in the usual way, it's just a state that's annihilated by all the A's. Then the usual one-particle states we get by acting with the creation operators. So these are labeled by momentum and polarization, lambda. But the states that we get from the time-like polarizations are very weird indeed. They're not something we've ever come across before in quantum theory because they have negative norm. Okay, so this is something very strange, right? We've got a Hilbert space, and the Hilbert space doesn't have a positive definite norm on it. So, you usually want to interpret, well, you usually want to interpret these things as complex amplitudes. And okay, you square it to get the probability. So you might think that, well, we're going to square it, so it's okay anyway. But actually, it's not true. This would lead to very, very curious things like negative probabilities. So that there's not really any good interpretation of Hilbert spaces with negative norm states. And it's clear what's happened, right? What happened was that we had these commutation relations, but the Minkowski metric of space-time, which was, had pluses and minuses, was appearing on the right-hand side of the commutation relations because the fields had space-time indices. And so there was no way to get both the spatial and the time-like components to be sensible. One of them was always going to give you negative norm states. So I've picked my choice of conventions such that the time-like ones suck, but the space-like ones were okay. Okay. So what we're going to have to do is find a way to deal with these negative norm states. But we still have a couple of things left in the bag. We've still got the fact that there's this relationship that's the Lorentz condition, d of a equals 0. We haven't used that anywhere. And there was still some residual gauge symmetry. So in the next lecture, what we're going to do is understand how we kill these negative norm states, or how we deal with them by using these two extra conditions that we haven't dealt with yet. Okay. Are there any questions about this? Yeah.
What is the interpretation of this norm?
The interpretation is that you want to get rid of it from your theory.
I'm not looking about the negative. What is the interpretation of the norm, the ground state, that norm?
Oh, and actually, it's true that what you have to do to compute probabilities is size the square. Okay?
Yeah, so we don't have a problem.
Yeah, so the difficulty comes when you include these states in sort of intermediate channels. When you insert like sums of unities where you put all the possible states, you're going to get minus signs in there, and that's going to screw up lots of things before you come to square. So you're right. You might think, well, we'll square it. We'll go. That's not going to work. It'll come and bite you when you start.
Also, these are just momentum eigenstates, right? So they should give something positive times above the function.
But more than that, I mean, all states should be correct. It's in the fabric of quantum field theory. We start with an ordered space that has some positive definite along. So we'll see how gauge symmetry rescues. But it's a common issue. All gauge symmetries have these kind of it's also worth saying the following. It's clear that these minus signs came from the Minkowski metric on the right-hand side of the commutation relations. And that was there because the fields had indices from mu and mu. Now, as you start working with higher spin fields, you're going to have more of these indices, mu and mu. The graviton is g mu mu. There's two indices. And you're going to get more and more negative norm states of the theory. And you're going to have to find new ways, inventive ways to kill them. Now, there's an amazing theorem due to Feynman and Weinberg from about the 1960s, these arguments were made, that if you want a massless spin-2 particle, the only way to get rid of these negative norm states is to introduce a new symmetry that is basically diffeomorphic invariance. So if you have a massless spin-2 particle that interacts, the only way to make any sense of that theory at the quantum level is general relativity. And you can actually derive the Einstein-Hilbert action starting with that assumption. If you want higher spin massless interacting particles, there's no way to do it. So these negative norm states, in fact, you've got to get rid of them to make any sensible theory. Are really wonderful things. And it leads you uniquely to, well, gauge symmetry is necessary in QED, and if the spin-2 particles, it leads you to general relativity, and for anything higher. So they're important ideas to get. Okay, I went over it. So,